All right, students, I have a question here from chapter 42. So I thought I'd make a video solution of it here. And it has to do with the Bohr model, really. This is well, there it is, the Bohr theory. It says that we have a hydrogen atom that's in the first excited state. So remember, n equals to 1 is the lowest state in what we call the ground state. And so the next energy level it could have is n equal to 2, and that's why they call it the first excited state, and then n equal 3, n equal 4. But it says here, using the Bohr theory of the atom. Now, without getting too much back into the lecture, let me just point out that the Bohr model is really not a complete model, but it's a good step in that direction. It's a step that what we often call kind of a semi-quantum theory or semi-classical theory, where we are saying the electron is a wave, so it's kind of a wave that goes around here. And so it still has kind of I'll even call it one-dimensional field because it just goes in a circle. The wave doesn't really oscillate inward or outward, and it doesn't go up or down. It just kind of goes in a path that is a circular path, but I'd still call it a one dimension. And so in this case, you might say that there's one wave, and then a second wave, and then a third wave. So this little picture is probably well represented as n equal to 3. And even though it's not a full picture, it is a good academic start because it does start to treat the electron as the wave. And that's where we had all that lecture on the neat stuff about it. Like, for example, one of the first things we saw after we used de Broglie's hypothesis that these electrons can be thought of as waves, then we realized there was this uncertainty principle that was a property of the waves. Then we realized that it's the property of the wave that makes things quantized. And then we realized there was a ground state that was non-zero. In fact, if we put that non-zero with the uncertainty principle, we realized that this was the reason the atom has a particular size to it. So it was Bohr who kind of looked at this and did a model that is not as complete as the Schrodinger's wave equation, because Schrodinger's wave equation is three-dimensional. So a little beyond the scope of this class, this is that first step where we're going to treat it as a wave, but we're still going to kind of treat it as a one-dimensional wave. It's just a one-dimensional wave where instead of being in a box going left and right, as we did in chapter 41, this is kind of a wave that's confined to a circle. So we kind of still say it has an orbital radius, and we can still label the quantum numbers. Surprisingly, even though this is not a perfect model, it is quite reasonable. In fact, question F might be the best question because this model, although imperfect for the hydrogen atom, actually gives you the same energies that you really get when you measure it, and the same energies when you do a more complete three-dimensional wave. So it's a good educational tool. All right, so let's work through this. Using the Bohr theorem for an atom, calculate A, the radius of the orbit. So remember, we're in the first excited state, so n equal to 2. It asks for a bunch of things: linear momentum of the electron, angular momentum of the electron, the kinetic energy of the electron, the potential energy of the system, that is the electron as it goes around the atom, and then the total energy. So that F would be the sum of E and D, the kinetic energy and the potential energy. All right, well, maybe I'll start with the easiest one. It would be A. And to kind of show this without kind of redoing the whole lecture, I'm going to grab the hard copy of the textbook. And notice I'm in chapter 42. I'm on page 1220 here. And here's where the Bohr model begins. It says an integer number of wavelengths will give us an angular momentum of this value. Then it says the total energy is kinetic plus potential. Then it writes the equation for kinetic energy, the equation for potential energy. It also then notes that those two have to be equal based upon the centripetal force. So this is the Coulomb force between them, and this is the 1/2 mv squared from Physics 121. And if you put all that together, you could see that the kinetic energy comes out to be this number. And the total energy, actually, if you look carefully, is the same numbers but with a negative inside of it. I'm going to take advantage of that. He goes on to show a couple more things, like here would be the velocity and here would be the radius. And that's where I'm going to go here, because that's the first question. What's the radius? So the radius of orbit n depends upon all these factors. So we could put in the value of h bar, the mass of the electron, Coulomb's constant, the charge of the electron, and then multiply it by n squared, whatever level we're in. Remember, the ground state n equals to 1, but we're interested in n equal to 2. So I'd put a 2 in there and square it and get 4. And your author actually does these numbers, so I'm not going to bother to actually put in the numbers for this video. I'll just point out on the next page. Page 1221, he calls it A naught. He puts in that h bar over m over Coulomb's constant, and he gets this 0.0529 nanometers and says this is maybe a better way to write out the radius of the orbit. It's n squared times that basic ground unit of radius. So in our case, it would be n squared. That would be 2 squared. So that's a 4. 4 times that number. So let me start there. So I would say, okay, the radius of the orbit is n squared times the radius of the ground state. All right. So in this case, it'd be 2 squared times the ground state, which is 4 times the ground state. And so 4 times in the ground state is this 0.0529 nanometers. So that looks like about a 0.2. I'll just grab my calculator and say, okay, 4 times 0.0529 nanometers, and come up with a radius of 0.2116 nanometers. So there's the first one. So there's A. I'll cross it off. And probably the easiest one. What's the radius of it? Now let me skip over B for a second because it says what's the linear momentum. And let me jump to C. Because C asks for what is the angular momentum. See, that's kind of where this idea started from. An integer number of wavelengths is related to the angular momentum. So there's the MVR from angular momentum. I guess it would be chapter 9. It would be back in Physics 121. But notice it's just an integer number of h bars. Okay, and this is the reduced Planck constant. So we're talking about n equal to 2. So all I have to do to get the angular momentum is put in a 2 and put in an h bar. You might write it this way. I'm not sure why the author didn't write it as this way, that the angular momentum is the quantum number. For those of you who took chemistry, we call this the principal quantum number. And so the principal quantum number times the reduced Planck's constant. So in our case, that's a 2. And if you remember, reduced Planck's constant is just Planck's constant, 6.63 times 10 to the minus 34 in units of joule times a second, divided by 2 pi. So I guess the 2's cancel off. And so to get the number for C, which would be 6.63 times 10 to the negative 34, and divided by a pi, and we're looking at about 2.11 times 10 to the minus 34, and the units would be a joule times a second. Those might look like funny units with angular momentum. They're really nice to keep that way, but for you guys coming from Physics 121, probably remember the angular momentum, and I'll just write that out. Remember, a joule is a Newton, so there's a Newton, times a meter, so there's a square, and then a seconds. So seconds would cancel off. And so the units would be, oops, I forgot the G for kilogram. So the units would be a kilogram, and then a meter per second times another meter. Okay? And so that's probably how you wrote your angular momentum units in Physics 121, MVR. However, I prefer, and most people prefer at the quantum level, to call it a joule times a second, because it's in the units that are used for h and h bar. All right, so there would be the angular momentum. Now, the reason I decided to do C first, not only was it easier, but we know then that angular momentum is linear momentum times the radius. That's the MVR for something going in a circle. And so that's the angular momentum. See, and we just did this for C and this for A. So in other words, to get the linear momentum, I would just take the angular momentum and divide by its radius. So its angular momentum is the 2.11 times 10 to the minus 34 joule over a second. Or maybe, if you would like, I will write it as kilogram meter per second times a meter. Because then I'm going to divide it by 0.2116 times 10 to the minus 9. That's the radius there in meters, so that meters cancel off. And I'm going to finish the problem then in units that we're used to for linear momentum, a kilogram meter times a second. Although, maybe since I'm introducing you to quantum mechanics, it's kind of nice to leave angular momentum as a joule per second. Then when you go to do linear momentum, you can write the joule as a Newton times a meter times a second. So when you divide it by a meter, they cancel off, and you have units which are equivalent, called a Newton times a second. Again, from Physics 121, you probably use that a little bit, especially with impulse, Newton times a second for the units. So whether you want to use kilogram times meter per second for the unit or Newton times a second, and in quantum mechanics we prefer Newton times a second, you're going to get your linear momentum. So let me grab my calculator here. Let's see, I still have the number in the numerator, 2.11 times 10 to the minus 30, excuse me, 4. Let me divide it then by 0.2116 times 10 to the negative 9 and come up with a linear momentum of 9.97 times 10 to the minus 25 in units of kilogram meter per second. And so there is my first three. All right, so maybe I'll cross out. So I got linear momentum and I got angular momentum. All right, so now the next three are really about energies. And I'm going to jump all the way to F. Because I mentioned that really F is the most interesting one about the... oops. Dropped all my papers. F is the most interesting one because this is the one that actually works out right. Now, your author first derives it back over here where he said this would be the equation, but he puts those numbers in right here, and he writes the energy in terms of a small unit called an electron volt. And so, again, those are kind of the preferred units when you're dealing with something small. So the total energy is this negative 13.606 electron volts over n squared. So we just have to put in the value of n. In fact, there's a little energy diagram right here kind of showing. So this when you put in 1, you would have a negative 13.606. And if you put in a 2 right here, this is this energy level, and we're gonna do this calculation, you're gonna see it's a negative 3.401. So really, we're done. That's what it is. But maybe just for completeness, I'll do it in front of you and get my calculator out here. So they're saying the energy for any given orbital n is minus 13.606 electron volts over n squared. And so we are in the first excited state, so n equals to 2. And so that is equal to a 4. So getting my calculator, I can put in a negative 13.606 and divide it by 4, and you'll see I get a negative 3.40, and you can round that to a 2 if you want. Your author chose not to, but that would be the energy. Now, that would be the energy in electron volts, maybe, if it makes you feel any better. And this will give me a chance to say what is an electron volt. An electron volt is a small amount of energy. It's equal to 1.602 times 10 to the minus 19 joules. That's why we like to use these electron volts as a unit of energy when we're dealing with quantum mechanics, because we're dealing with small little things, and a joule is just way, way, way too much energy. So electron volts is a more appropriate unit of energy. But to make it in units that maybe will have you feeling a little more comfortable, let me just do a unit conversion. And so right here, I'll just replace what an electron volt is equal to, and then do the math. So I've got the negative 4.402, and then so times 1.602 times 10 to the negative 19. And so we're looking at a negative 5.45 times 10 to the minus 19 joules. Either one is fine, either in units of electron volts, which probably, when we look up the answer, is probably going to leave it in electron volts, because they're trying to get you to feel a little more comfortable with electron volts, just like probably when it comes to the angular momentum, it'll be in joules times second, not a kilogram meter per second times a second. Okay. All right, so there's the total energy. But the reason I thought I would do that one first, so I'll cross off F, is to jump back up here to D, which is the kinetic energy, so D, and to come back into this derivation, and I'll point it out again, right? We see that the kinetic energy numerically has the same value as the absolute of the total energy. So the total energy is a negative one, so we got to kind of go back to our satellites and our planetary motion, Physics 121, where we did, I think that was chapter 13, and we had a negative potential energy and a positive kinetic energy, and we brought them together. Since the negative potential energy was a little bit more, the total energy was slightly negative. In other words, 0 actually represented where the spaceship or the satellite was completely freed or separated from the planet. So 0 energy is quite a bit, and it's a separation. So an electron will always have a negative energy. Of course, you can see it in this formula. Or maybe I should say an electron that's always trapped in the atom, just like a satellite, always trapped going around the Earth, always has a negative energy, because to completely break free gets it all the way up to 0 energy. Now, if you break free and you move, then you have positive energy. So the neat thing about 0 energy and positive is it tells you it's free and breaking apart. And of course, for an atom, we know that the electron is stuck. So we expect to always have negative energy for any quantum number n. And sure enough, with an equation that says minus 13.6 over n squared, give me any value of n, and it's still a negative number. And so as long as the electron is still bound to the atom, even if it's in a very, very high excited state, like n equal 100, it's still negative, although barely negative, and it wouldn't take much to break it free and make it go zero. Or if it goes positive, not only does it break free, but as it moves away, it continues to have a positive amount of kinetic energy. So again, that's why this number comes out to be negative. But to answer this question then, the value of the kinetic energy is really just the absolute value of the total energy, and that'll make calculating the kinetic energy very trivial. There it is. It's a positive number. Or you could say positive 3.402 electron volts. So that's pretty easy. And then E, the last one, which is the potential energy, is also very easy because we know kinetic energy plus potential energy is equal to total energy. Okay, and as we already said here, the total energy is a negative of the potential, or maybe I'll put it this way, negative of the kinetic. So I would do something like this, E minus the kinetic. So that's what we would really say here is the E, really, there's two E's here, I guess. There's one here, and this magnitude's the same amount. So since we've got a negative here, and the kinetic energy is then equal to the negative of the E because of the absolute value, you could then just write this as 2 times the total energy. Although I'll just put in the numbers. So I'm going to put in a negative, and maybe I'll do electron volts. So the total energy is negative 3.402, and then minus the kinetic energy, which is 3.402. And so if I put those together, I get a negative. The 3 and the 3 make a 6. The 4 and the 4 make an 8. 0 and 0, 4. And so there's my electron, in electron volts. And then I could convert that, if I wanted, into joules. But I'll even take an easier way out. Why don't I just take what this value is and then realize that the potential energy would be the negative of doubling that. So if I double a 5, I get a 10, and if I double a 45, I get a 90. Then I suppose if I want to make it scientific notation, I'll move the decimal. And of course, then making this smaller means I have to make that one bigger, so 10 to the minus 18 joules. So this would be the potential energy. All right, hope that helped. Bye now.